Two of the most advanced rocket engines ever built sit on opposite ends of the same mission, getting humans and cargo off the surface of the Earth, and yet they barely have anything in common. One was built in the 1970s for a government space agency with a budget that dwarfed entire countries. The other was built decades later by a private company, obsessed with driving costs down instead of up. To understand why SpaceX's Raptor and NASA's RS-25 look, sound, and behave so differently, you have to start with the fuel each one burns. The RS-25 burns liquid hydrogen and liquid oxygen. This is often called the cleanest and most efficient fuel combination in rocketry, because when hydrogen and oxygen combine, the byproduct is simply water vapor. Hydrogen also produces an extremely high exhaust velocity, which means the engine gets more performance out of every kilogram of propellant than almost any other fuel combination available. This is part of why the RS-25 was chosen to power the space shuttle, and later, NASA's Space Launch System. But hydrogen comes with a serious downside. It has to be stored at incredibly low temperatures, colder than almost any other rocket fuel, and it takes up a huge amount of volume compared to how much energy it actually contains. That means bigger fuel tanks, more insulation, and far more complexity just to keep the fuel stable before it ever reaches the engine. Raptor takes a completely different approach. It burns methane and liquid oxygen, a fuel combination sometimes called methalox. Methane doesn't produce quite as much raw performance as hydrogen, but it solves several problems that made the RS-25 incredibly expensive to build and maintain. Methane is denser, so it needs smaller tanks. It doesn't require nearly as much insulation. It burns cleaner than kerosene, which means less soot and residue building up inside the engine after each flight. And critically, methane can theoretically be produced on Mars using local resources, which is a major reason SpaceX chose it in the first place. Raptor wasn't just designed to get to orbit. It was designed with an eye toward eventually manufacturing fuel on another planet. The differences don't stop at fuel. The way each engine actually burns that fuel is where things get even more dramatic. The RS-25 uses what's called a staged combustion cycle, which was considered extremely advanced when it was developed. In this design, a portion of the fuel and oxidizer is burned early in a pre-burner, producing hot gas that spins a turbine, which powers the pumps that feed propellant into the engine at high pressure. It's an efficient and powerful system, but it operates using something known as fuel-rich staged combustion, meaning the pre-burner burns with excess fuel to keep temperatures manageable for the turbine. Raptor goes a step further, using what's called full-flow staged combustion, one of the most difficult rocket engine cycles to build, and one that had never been successfully flown on an orbital rocket until Raptor did it. Instead of one pre-burner, Raptor uses two, one burning fuel-rich and one burning oxidizer-rich. Every bit of propellant passes through a pre-burner before reaching the main combustion chamber, which means the entire engine runs at extremely high pressure with far less wasted energy and far less thermal stress on any single component. It's more efficient, more powerful for its size, and remarkably, better suited to the kind of rapid reuse SpaceX wanted to achieve. The RS-25 was designed to be reused a limited number of times with extensive refurbishment. Raptor was designed to be reused dozens of times with a small fraction of the workload. That difference in mindset explains almost everything else. The RS-25 was built during an era when NASA prioritized peak performance above nearly everything else, spending enormous amounts of time and money to build a small number of extremely refined engines. Raptor was built during an era when SpaceX prioritized mass production, rapid iteration, and low-cost reusability, aiming to eventually build engines the way a factory builds cars, rather than the way a workshop builds a single masterpiece. Neither approach is simply better than the other. The RS-25 remains one of the most efficient rocket engines ever created, and it still powers NASA's most ambitious deep space missions today. Raptor represents a completely different philosophy, one built around the idea that spaceflight only becomes sustainable if the hardware can fly again and again without being rebuilt from scratch every time. Two engines, two eras, two philosophies, both chasing the same goal of leaving the planet, but doing it in ways that couldn't be more different.